So again, welcome everyone. I wanted to just start by putting us back in the context of why we're doing all this. So this is at least one big why. The whole planet is working on sustainable development goals. We began this process in 2015, and they are, as were the Millennium Development Goals, quite lofty. That we're working on all these things. There are 17 different tasks, like themes of things that we're supposed to be working on. And the one related to drinking water, which is number 6 there, clean water and sanitation for all. Here's the challenge. There are at least 1.8 billion people use a source of drinking water contaminated with feces. That's one, unfortunately, astounding number. And maybe a related number, more than 80% of wastewater on the planet is discharged without any pollution or any treatment, without any pollution removal or treatment. That is just like, so we didn't talk about wastewater at all in this course, but could you imagine this? There could be a companion course where you do the exact same thing, working on developing wastewater treatment technologies that would work well for small communities. It would be an amazing course, and there is a ton to learn on that side too. And just like on the drinking water side, there'd be a ton of opportunities for developing better technologies and slowly making a difference. Okay, so the goal is Sustainable Development Goal, safe and affordable drinking water for all by 2030. The claim is that something like 3 out of 10, 30% of the planet, 2.3 billion, lack access to safe and readily available water at home. And I just wanted to put in there Monroe's skepticism, which is one of the things that we value, right? We value skepticism, and I want to put in there its skepticism. It's not clear if those numbers are guesses or if they are based on real data. And the reason I hold that skepticism is because if you would look at the numbers for a country like Honduras, you would find out that according to their numbers, the majority of Hondurans have access to safe drinking water. And yet, when you go to Honduras, you have a hard time finding where those places are, where they have safe drinking water. And so there seems to be a real lack of connection between the reported numbers and what's actually truth on the ground. And then if you take into account that there's going to be population growth over the next years, you can come up with these crazy numbers that basically we need to provide 267 million people per year with safe drinking water. That's like providing safe drinking water for the entire country of Indonesia every single year. If you use the kind of water consumption that is typical here in the US and also is typical in places where people have access to water, like at their houses on tap. If you have access to water on tap in your home, you tend to use something like 3 milliliters per second per person. That's a fun number to remember to do some quick calculations on how much water is needed for a city. So if you have a city of 10,000 people, every person in that city uses 3 milliliters per second. So with 10,000 people, you would need 30 liters per second of drinking water treatment capacity to provide them with water. You would also need some reserve capacity to handle fluctuations, but 30 liters per second on average every day is what you would need to provide. So at 3 mLs per second, we need 800,000 liters per second per year of new installed capacity, assuming that all these folks need drinking water treatment plants, which may not be correct because some of them are going to be using groundwater, well water, and might not need treatment. But just like, no matter how you cut this, the demand is huge, the need is huge. And then for our own story, the Agua Clara story of how we got in on this game, this is from Jacobo Nunez, who is the director of Agua para el Pueblo in Honduras. And he asked me, of course, in Spanish, what can we do to treat the dirty water that we are providing to rural communities? And that was one of the questions that got me thinking about this problem. That was back in 2004. So the problem is that many people have access to river water on tap. So river water coming out of the kitchen sink, which might look fine during many months of the year when there isn't much rain, but when rainy season is there, you can really see that the water is dirty. And even when you can't see that the water is dirty, it still very likely has high concentrations of pathogens, because there are most likely people living upstream. Certainly there's wildlife living upstream if there aren't people living upstream. And so there's chances for all kinds of fecal contamination. And that results in people being sick. That results in especially children. The critical time period for children is between birth and 5 years, between birth and 5 years of age. That's when children are most vulnerable to getting sick enough from diarrhea that it causes them either severe malnutrition or even death. So that's the most vulnerable population that we're most worried about. And then we do this based on some empathy. Like we think about, what does it feel like? What is it like to live in a household where the only water coming into the house is river water? And what is it like to try to wash dishes and clothing and children and keep the children safe? And I argue that you need to be a microbiologist and think about aseptic technique in order to think about how to try to keep your children safe when the water that you're using in the household is very likely laden with pathogens. And this is all why we're working hard to develop better technologies for making safe water on tap more accessible to more people on the planet. Okay, that was my pitch for the beginning. And I'm thinking now is the time I would love to hear from each of you a sentence or two of what's one thing you learned. And you don't have to be trying to think of the most important thing or the one thing you're going to remember a decade from now, but just one thing that you learned. And what I don't know is how to go around in some relatively efficient way. I suppose what I propose is I will randomly call on one of you to start this, and then each one of you, when you're done, you name the next person. Okay, so it's like we're passing the talking stick around. I pass the talking stick, it's this planet Earth. I toss it to one of you, and then you toss it to the next person and give them, you give them the ball. So I would love to start with, oh my goodness, so many good people to ask, and I don't know who to talk. I will call on Katie.
There's a lot I learned, obviously. I would say like the biggest thing I learned, or like something I'm very conscious about, is that there's a lot of things we don't know about how filters work.
Okay.
And I'll call on Tony.
I learned what an LFOM is. I had no clue what the linear flow orifice meter was until this class, which was cool to learn. I'll pass it to Ravi.
One thing I guess I was most interested in learning was flocks themselves can be filters. So that was something interesting to me. I'll pass it off to Eric.
I'd say the biggest thing that I learned coming in, which was very limited amount, was how many systems kind of work together to make a complete system and create the cleanest water possible, and how those systems can change just with something as like higher flow or lower flow or anything like that, how they can change an entire system, which was very informative and interesting. I will pass it to Mackenzie.
I think the one thing I learned was just how it's kind of pointless to only use a filter to filter water. Like one filter itself isn't actually going to be that effective if it's very turbid water. So matching it with a clarifier is super important, but that's something I never considered before. So yeah, and I'll pass it to Dan.
Dan, you're muted.
Sorry, I have a physical mute button and one on the screen. I was going to say something similar, but I'll add to it. I liked that moment where you said, like, would we use a filter or would we use water treatment like flocculation or clarifying? And we all were like, filtration, obviously. And you're like, no, we get clogged instantly and be terrible. That was a fun moment. But I also liked when we learned about how flocculation creates its own filter, that they themselves are their own undoing, right? That they tumble back down and filter the other ones coming along. So that was a neat moment. And I will call on Michael.
Yeah, for me.
Oh no, Michael.
Hey,
Like,
I think that every time. But this time's mine. I think for me, I was scared going into this course, not knowing much about how the process works for clean water. And like Eric, seeing how all the parts, all the systems go together and work, I feel like that was really fascinating to me, especially seeing that through the on-shape programs that we worked with. And I will call on Isaac.
Yeah, I would say the biggest thing I learned was actually a relearn, because I took fluids during like peak COVID when school was an interesting process or time in life. So I think relearning a lot of the basic concepts of fluids were really important going into post-graduation. And I will throw it to Mr. Preston Newkirk.
Thanks, Isaac. I would say, piggyback off what he said, I really think this class kind of helped me visualize head losses, and I was able to incorporate that with a lot of my other coursework this semester, which was really great. And turbidity, high, low turbidity of water. And I will pass it off to Brendan.
So one thing I learned was that water flows by piezometric head and not necessarily by elevation. And I will pass it on to Victor.
I would say one of the biggest things I learned was about that stacked rapid sand filter. I think it's interesting that like technology can be improved upon no matter what the case. Like I just feel like the standard in the US is just, that's what it is. And that's what we learn. But learning about different systems and how you can kind of make your own system over time, just that was interesting to me. I'll pass it to Finn.
I think the broadest takeaway for me, Dan and Mackenzie kind of already talked about this, but just the fact that the majority of the cleaning of the water occurs way before filtration, which is something I didn't know before this class. But since that was already said, another big thing for me is just like the power of using programming and code to sort of integrate with a 3D modeling environment, and how that can save you a lot of time when you're trying to model anything like the plant.
And who should we pass on to next?
Yeah. Sorry, I will pass it to Hannah.
I think one of my favorite things that I learned about was the flocculator and how flocks are formed, kind of piggybacking off of Ravi, and how fragile those can be compared to like the velocity, and how easily they can just fall apart. And I'll pass it off to Steph.
I was gonna mention, like Victor said, the stars filter. I had no idea that sand could be used at this capacity, so I think that was something really cool to learn for myself. And I'll pass it off to, I don't know who hasn't gone yet. Jin Yao.
Maybe not there, or so did we get all the students now? Okay, I want to give the other participants in the course a chance to answer this question too, if they would like. So I want to pass it to Izumi, and then we can go to Claire and Michael and Patrick.
Sure. I really enjoyed the chances that we had to look at different ways that water treatment had been designed and just like poke holes in it and be like, oh, when you would ask us, what are ways you think this could be improved, or what are ways that like this is going wrong? I thought that was really helpful to view possible solutions and then see how those solutions have been incorporated into Agua Clara plants, or how like Agua Clara is currently thinking about how to improve them. And what I learned from that is that it's always good to go back and review your designs and make sure that the math checks out and that everything makes sense and is working as well as you hope it can be in the moment.
Thanks, Claire.
So I guess the cool thing for me is that it was 4.5 years ago when I took this course. And so to be able to see all of the things that have changed is what's been cool for me to learn. The one diagram that really sticks out to me as being new was the one of the clarifier that had the blue guys and the red guys and the green guys. And it's now we know where all of these things are happening. And these guys, I sure hope that wasn't included 5 years ago. Otherwise, I just didn't remember it. But those insights were all new. And so those were all things that I learned this time around.
Cool. Michael Hagenberger.
So for me, I was most intrigued by the student learning, and in our capstone course, we had a student group working on the structural design of the plant. And so for me, it was extremely rewarding to see the connections between the class and the capstone. And we made so many discoveries that were intriguing throughout the way, throughout the entire semester. And for me, I always knew it was smart, but there's also a lot of complexity to how smart the system is, which for me was really unveiled as I was taking the pieces apart and figuring out how it stands up. So while I always appreciated the smartness of the technology of the water treatment, seeing how it came together and packaged in the way that it was also pretty fascinating to me. So.
Thanks, Michael. Patrick?
Sure. I think a few things come to mind. I think one, having seen the diagrams of these plants for so long, finally being able to make one and look at one in Onshape and move it around and like really get how all the pieces fit together. That was pretty exciting for me. And then also just seeing, I've always been very impressed with the plant, but I think now I'm even more impressed with just the amount of thought, kind of building on what Michael said, of the intricacies of this design. And I think I realized I thought I knew how it worked and I did not. And now I maybe sort of understand how it works, but I feel I'm still learning too. So.
Yeah. Wow. So thank you all. Thank you so much for sharing those learnings. It was really fun for me to hear them, and I'm hoping it was enjoyable for all of you. And this just makes this insight of, okay, Patrick and Michael have been very kind in talking about how smart the design of the Abraclata plant is. And I want to credit some of that with the fact that I've been teaching a course every year for like 17 years, describing what we knew about the design. And so one of the things that I learned again in teaching this course, which I hadn't done for several years, is that every time I teach the course, I'm forced to once again try a little bit harder to make things a little bit clearer and make sure that I capture the latest things that we've learned and included in the lecture. And that evolution is both good for teaching, and it's also good for the design. And maybe that's one of the reasons why designs have not continued to evolve as fast as they should have in kind of the standard approach to designing water treatment plants, is because the folks who have been designing those water treatment plants haven't been teaching a course about the underlying physics of their design. Maybe if that had happened, they would have continued working on improving them. Anyway, that's something just to think about. Okay, I've got a few minutes, and I have some slides that I put together that I want to go through. So let's go on a trip, okay? So thank you for answering what did we learn. I'll do my take on just like this real quick review, because you don't get an exam, so you got to at least do a review. So we did flow control and measure. We realized that we need constant chemical level in order to get constant chemical flow. And we know that the stock tanks, the level is changing over time as the stock tanks empty. And so we use a very simple device, a float valve, to get that constant level. We use dosing tubes to turn that constant level into a constant flow rate. Those dosing tubes use laminar flow and a long, straight, small diameter tube. And that gets us a linear relationship between an elevation change and that flow rate. And then we use the linear flow orifice meter. Was it Tony that mentioned this? And that provides the easy linear relationship between flow rate and water level going through the plant. And then flocculation. So this is a place where there's all these energy conversions, and ultimately that energy conversion does something that we need, which is collisions between particles. But it starts with, there's a potential energy difference across the flocculator. That potential energy is converted into kinetic energy through flow contractions in the flocculator. And then that kinetic energy is converted into heat. And on the way that does that is through viscosity. And the way viscosity does that is by deforming the fluid. And it's that fluid deformation that ends up dragging the particles with it. And that fluid deformation, hence that causes collisions between particles, which is what we actually wanted. So there's this long story of energy transfer, but the bottom line is, in the end, the water deforms, that causes particle collisions, and that's what we need so that particles can grow. And then GT is kind of a measure of the total fluid deformation that happens in a flocculator. And so you know that you need lots of fluid deformation, so you need a high value of GT to get lots of collisions. And then you now know the equations for designing the flow dimensions to get that a target velocity gradient, and you know how to figure out how many contractions or expansions you need in order to get the total GT in order to get your desired treatment. Clarification. So we use diffusers and a jet reverser to keep the flock filter fluidized. So now you saw a fluidized bed of sand on Tuesday. There's a fluidized bed of flocks. We call that the flock filter. They're not nearly as dense as sand grains, and so it's much more gentle, but it's the same idea. And it, just like the sand had a clear interface between the fluidized bed of sand and the water above it, the flock filter has a very similar thing where there's lots of flocks and then all of a sudden it's almost clean water above it. Those flocks in the flock filter capture small particles that failed to flocculate. Excess flocks flow into the flock hopper, and then particles that settle faster than the plate settler capture velocity are converted into larger flocks by the plate settlers and then return to the flock filter. And so there's this lovely dance of particles happening within the clarifier. And then there's a filter, which I tagged here, which you can use if you have clean water. Larger flocks that attach to the constricted part of a pore formed by sand grains end up being filters that capture small particles. So even within the filter, the sand filter, flocks end up playing a key role as being the flock filters. The flocks have a finite capacity to capture small particles, and also constrictions don't clog. They just reach a stable minimum diameter where the shear exceeds the coagulant bond strength, and then flocks that come in just blast right through those pores and continue deeper into the filter. And eventually that active zone in the filter where flocks and other particles are being removed, that slowly migrates down in the filter. Eventually it comes out the bottom, and at that time you see extra particles coming out the bottom, and we call that breakthrough, and the filter performance worsens. Okay, so that was, goodness, that was the whole course, just like that, boom. Now let's zoom out one step. So, there's a plan, but we're gonna zoom out and we're gonna think about some other things that happen in this class. So we learned about—
No, we can't see your screen. So
how long has—
the whole time, but you explained it all, and so I assume everyone knew what you were talking about, but when you just indicated, now we zoomed this out.
That's fascinating. It says I'm screen sharing.
I can see the screen. Well, now I can't, but I could before.
Okay.
Oh,
Okay,
might just be me then.
I feel better because I was getting the right— okay, so we're all back online?
Yeah.
Okay, great. Okay, so we learned about parametric design and the power of parametric design. And this is just like a very quick outline. We have this insight that humans have much to learn about how the universe works. And I want to like couple of my pet points, happy points. Technology matters, and a sense of multipliers, and a little bit about US drinking water infrastructure. So the power of parametric design. You learn to codify the logic of the design, create the general solution rather than a specific solution. So in each of your design challenges, you had an option of changing a flow rate at the end of your design, and you would get different answers calculated automatically, and it would be another viable solution. It's as if you did the general solution for that design challenge. Now you have, once you've done that, you have a tool that can create customized designs. And if you learn that there are additional constraints that maybe you missed in your first design, you can change the configuration, edit the logic to capture the new constraints, and all of a sudden you'll have a new whole set of designs. This is the power that Agua Clara is really enjoying. Now, we have all these designs, we have the code to create them, and we can, as we learn new things, we can very quickly modify that code and put that right into the designs that are being built. And I want to make it very clear that parametric design is not something that, oh, it makes sense to use for Agua Clara plants, but that's it. No, this is a tool that can be used in many, many places. Whether you're thinking about wastewater treatment plant design, or bridge design, or home design, or designing solar farms, or designing windmills, like wherever you want to go, if you're designing something, the idea of creating a parametric design to solve the problem would be very, very powerful. Another thing that we have been reflecting on is that the edge of knowledge is very near. We have, as humans, we have major gaps in our knowledge. There are many things that we don't know. And the way I like to think about it is that of all the things that one could possibly know, each of us knows just a tiny, 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 tiny little bit. So the vast majority of things I know nothing about. I know a little bit about drinking water treatment, and the little bit that I know, I realize means that there's much, much more about drinking water treatment that I don't know yet. So holding that as both a little bit of humility and the power of there's so much more to learn. And if we do learn more, we can do even more things. So this is a quote out of our textbook. We want to encourage skepticism, and we want to develop insights to guide thoughtful skepticism. A key skill for successful engineering is the ability to identify the location of the edge of knowledge. It is much more powerful to know where the edge is than to just be overly confident and not be aware that we're in territory where we don't know what's going on. There are so many opportunities to continue to improve drinking water treatment technologies. I made it very clear that we don't fully understand what's going on in the flock filter, and I would argue that no one has ever really figured out how to optimize operation of a flock filter. Sand filters, the same thing. Yeah, we've been using sand filters for 100 years, but we don't really understand all that's going on inside them. And because of that, we don't have equations that describe how we would design them and make them better. And indeed, the stacked rapid sand filter opens up a whole new opportunity for thinking about filters in a new way. And very clearly, we have not optimized that. A whole other domain is thinking about plant operation. We're currently embarking on this path of figuring out how we might start providing good feedback to plant operators about what they should do with coagulant dosing. That's been a dream for very, very many decades. And my suspicion is that there's at least a good chance that we can crack that one, because we finally have better insights as to what's going on inside the plant and what role the coagulant is playing. And if that wasn't maybe a bit of a surprise, if you were in a conventional water treatment course, you would have learned a completely different explanation for how coagulants work. So what we learned here about coagulant nanoparticles is based on our research, laboratory research, papers that we published, and being the first ones to develop a model describing flocculation using equations. And we use a scientific method to test hypotheses. And I just had this fun conversation with Minty Nunez, who is an engineer working with Agua para el Pueblo in Honduras. And she sent me a WhatsApp message and she said, should we assemble one of the clarifier manifolds without tapering the diffusers? So remember those tapered diffusers? And she's like, so when we're making this next plant, should we have one of the clarifiers not have tapered diffusers to see how it works? And of course, my answer was yes, let's do the experiment. And it is relatively low cost and relatively low risk. And so we'll learn if the tapering is necessary or not, and whether it's actually better without the tapering. So we will continue to learn. Stay tuned. And here's another insight. Useful technology is in many circles an undervalued factor. I visited lots, well, not lots, but yeah, a lot of water treatment plants in many different countries. And it became clear from my visits that technology failures are common, and that technology is a major reason why water systems aren't working well. Okay, one of the current stories about why water quality isn't good when it arrives in the tap in the households is that the water is contaminated by the distribution system because the pipes in the distribution system are old. It is possible that that is right. But I turn on my skepticism and say, given what I have seen in many countries and in many water treatment plants, I suspect that it is much, much more likely that the reason that water often doesn't come out of the tap safe is because the water treatment plants aren't working well. And that requires a very different solution. So, be skeptical. I don't know. I'm just skeptical. I don't actually know what's causing the problem, and you'd have to do it on a site-by-site basis. But just because people with confidence talk about distribution systems making the water quality fail, doesn't mean we should believe it, because we also have, like I have firsthand evidence that water treatment plants aren't doing what they're supposed to be doing. And then this other insight, good technologies are worth money, and they make the whole system more sustainable. So people are willing to pay more for quality services that they value. No one likes to pay for dirty water on tap. People are willing to pay more for safe water on tap. And if the incremental amount of value that people place on having clean water, if the incremental value that they place on it exceeds the incremental cost of providing safe water, then making that change of providing safe water will actually make the entire system more sustainable, because there will be more revenues now than there were before. We've seen this in communities in Honduras, and I suspect that this is something that could be replicated in many, many places. There's one equation for today's talk, and that is 1 times 1 times 1 times 1 times 1 times 0 is 0. And so this equation captures the idea that in order for a system infrastructure for a community to be successful, all these things have to work. There has to be an energy source, assuming that it needs some sort of energy. It needs an energy source. It needs to have some education in the community about what this system is and why it matters and why they should help pay for it. There needs to be money to pay for it. There needs to be some form of governance, both locally and a nationally supporting governance structure that makes it possible for this infrastructure to work. There needs to be a pool of labor. There needs to be people who are able to do the work that needs to be done to maintain the system. And of course, there needs to be money, mentioned earlier, to pay them. And there needs to be some technology that is the infrastructure that you're going to provide. And if any one of those factors is a 0, the system isn't going to work. And of course, if technology is a 0, it's not going to work. And as an engineer, the cool thing that I think about is I'm not wealthy. I can't pull a Gates thing and independently fund providing safe water to lots of people. But if I can use my brain and engineering and my ability to generate community to create better technologies so that communities can use this new technology and pay less money than they would have for previous options, then it's as if I had generated that capital, right? By generating a better technology, I can reduce the need for capital and can solve the problem, still get the same, we get to success, even if there's not as much money available in those communities. And I wanted to, maybe you saw this from me before, but I wanted to remind you all of this tendency as engineers to blame others for our failures. This is just a human tendency, right? We would like to blame others for our failures. And so here's a water treatment system where the characterization was that the community didn't maintain their water filter plant, but that implies that there was something that the community didn't do that they should have done. And it implies that maybe the community didn't make a rational decision, that maybe the community should have maintained a system, but they didn't. And so here's some reflections about, well, why might this community not have maintained their water filtration system, their water treatment plant? So maybe the community didn't value clean water, or maybe there wasn't a mechanism in place to fund operation and maintenance. And so we got a 0 on that one. Or maybe it was just too expensive to operate, or maybe it was too hard to clean the filter, or maybe it takes too much water to clean the filters, or maybe they were never trained how to do it. Or maybe the filter didn't clean the water. In that particular case where there was this water treatment plant that was built for a town in Honduras, that system could not have made any significant improvement to the water quality because they weren't using a coagulant, they only had a filter, and they were treating really, really dirty water. So it could not possibly have worked. And yet, in telling the story about that system being abandoned, people didn't talk about it was a technological failure, and it was. Instead, they talk about the community didn't maintain their water treatment plant. So it would have been much, much better for the engineers to say, you know what, that was an engineering failure because the technology didn't actually work in that context. Okay, and now the US water infrastructure. So you're getting, some of you are graduating shortly, some of you are graduating next year sometime, and you're getting grades that are better than this, right? The American Society of Civil Engineering drinking water grade for US water infrastructure is C-. You can go check it out at their website. What you've learned in this course is completely applicable to designing new and upgrading existing water treatment infrastructure anywhere on this planet. It's the same physics no matter where you are. Granted, you will be pushed to do more conventional designs that don't work as well here in the US, but now you know some of the underlying physics of what's going on inside water treatment. And so you are positioned very, very well to work on any of this design work. You have the latest insights into the core water treatment processes, and this is the only course on the planet that teaches these ideas. So you have a competitive advantage. And by the way, employers like consulting firms love having students come out with this background. Resilient designs are needed in the United States too. Fewer interdependent systems are better. So real quickly, a story from New York City. I know this was a long time ago. It wasn't before I was born, but it was a long time ago. 1977, there was a blackout. All of New York City lost power. And one of the engineering insights from that event was that there were gas-fired turbines that could generate electricity that could be brought onto the grid very, very quickly to provide power. And New York City should have been able to use those to get started again after they lost power. But there was a problem. Those turbines needed lubrication for their bearings. And they had an oil pump to circulate oil that needed to be running before the turbine started. And that oil pump was driven by an electric motor. And so they couldn't start those turbines with the grid down. So just think about, this is a great insight for engineers. Think about startup and shutdown. It's very, very easy to continue along when everything is working well, but think about what's it like during startup, shutdown, and extreme conditions. Here's another one, Boeing MAX 8. It's not been in the news lately because pandemic and other things put it out of the news, but it was a big thing just a few years ago. And the reason that MAX 8 failed is because they substituted a stable aeronautic design, and instead used software and feedback to control the plane. Previously, planes were designed so that the engines were located in a place where the engine could thrust really hard and it didn't create any unstable forces on the plane. Boeing Max 8 violated that rule, and they tried to compensate using software, and that's what led to those failures. And I love using computers. I love using computers. I love using computer control. But I think we need to be smarter about how we're doing that. I think we should think about, yeah, you can read those too. Using computers to manipulate valves to set flows using feedback control results in poor performance in many modern drinking water treatment plants. This is a big issue, and there are many plants where the plants were previously had nice hydraulic controls, which is, think about how Agua Clara runs water through a plant. Those plants had hydraulic controls, and they switched to get rid of the weirs, get rid of the elevation controls, and instead stick in a mechanized valve and use a computer to control how much that valve is opened and have that valve controlling the flow rate. Those systems, like theoretically, they could work, but the feedback control ends up causing flow oscillations. And just 2 days ago, I was looking at flow control through a municipal water treatment plant filter and seeing the filter flow rate doing this, just up and down, up and down, up and down because of bad computer control. So there's a good argument for using the hydraulic control system that Agua Clara is using. And then putting on top of that smart computer controls, but leaving the core operation to make sure that the plant does what it's supposed to be doing to the more simple hydraulics. Computerized controls require experts to tune the algorithm and to maintain the hardware and software, whereas hydraulic controls can be easily designed to reliably accomplish those same goals, set it and forget it, and the same plant operators who are working in the plant can easily understand and operate and fix as needed those reliable hydraulic systems. And then this is just from a word from the folks in Honduras, granted it's from 2019. There was a rural water workshop. The Agua Para El Pueblo engineer Santiago Garcia gave a presentation about Agua Clara technology, and they went and visited a plant. And then Pedro Ortiz, who is like the Honduran government water ministry top water engineer, stated that the only group in Latin America that is investigating low-cost water treatment is Agua Clara. And he called it la mejor en el mundo, the best in the world. Just a couple more things. I want to think about how you can connect meaning to graduate school and professional careers, because some of you are moving on in a few weeks. So for those of you who are thinking about graduate school, and when you're connecting to graduate programs, think about what kinds of research you're getting into. There are 4 steps that are often used during graduate study. One is measure stuff. And there are PhD programs where you can measure stuff, and that's all you need to do to get a PhD. The next level is to create models of how our universe works based on those measurements. And that's fundamental science. And that's one step up, one big step up from just measuring stuff. Take it another step. You could take those new understandings of how the universe works and you could invent new solutions. So that's another big step up, inventing based on how the universe works. And then as another step, you could take those inventions and you could engage with the world to implement those solutions. That's engineering. So in this, you can measure stuff, you can figure out how the universe works, you can invent new solutions, and then you can implement those solutions to make the world a better place. That's kind of the the steps towards and steps towards seeing engineering as the culmination, right? Engineering is the last step. Our planet needs bold engineers and scientists who engage and can create a better world. And I want to end with one more thing. Happiness is safe water on tap, and engineering is love. So engineering is love is making this connection that engineering makes it possible for people to live and thrive in communities. The only way you can have a city where people are healthy is if there's lots of engineered infrastructure that helps support that. So the engineering that's required to help those communities thrive is about love, because helping others to thrive is the definition of love. So designing and building the infrastructure that makes it possible for communities to thrive is love. And now some thank yous. A big thank you to Patrick Sowers and Michael Hagenberger for creating the dream of an Agua Clara program at OSU. Special thanks to Patrick for making teaching easy by handling all of the administrative and logistical details. Special thanks to Claire for making this first Onshape version of SWOT a success and for providing lots of feedback and guidance to all the student teams. And thank you to all of the students for being willing to take the risk of a new course and taking the risk of learning lots of new things. So thank you. I really enjoyed teaching all of you and getting to know all of you at least a little bit. And you now know where I hang out in Onshape. And so you're welcome to stop by and visit me anytime. And of course, if I'm not there, you can send me an email or chat and make connections with me. Claire, if you could send the link to the survey, you've still got 20 minutes and that ought to be perfect for filling out this survey. I would ask that you all do this survey right now. It's like your final, it's not your final, but think of it as this is your final task for the course. Fill out this survey, give us feedback and give us like your most honest feedback about what worked well and what didn't work well, what we could improve. We really appreciate that. Any other last words? I'll turn it to Patrick.
I'll just add, we appreciate all of you taking the class and working with us as we figured out how to run the first remote class across you all and other folks joining in. So I'm excited to keep offering these. So thanks for being part of it.
I'll extend a thank you to Monroe for being willing to try this. Couldn't be happier that after meeting years ago that it actually finally happened. And I thank you for doing it. It was great to watch it this year when I could get here.
Great, thank you for the invite. Okay, you've all got the link to the survey. Go for it. And I'm going to say goodbye, but I would be delighted to have you stop by and say hi sometime. So I'll tell you what I'll do. I've got 20 minutes. I'll go stop by in Gather. So if you want to stop by there and say hi and bye, welcome to do that. So I'll see you in Gather if you want to stop by. Bye, everyone.